In section 8.4, we prove the converse of the Rate-Distortion theorem. Here is the idea. The Rate-Distortion theorem says that Rd is equal to Ri of d. We will prove that for any achievable Rate-Distortion pair Rd, R is greater than or equal to Ri of d. Recall from definition 8.13 that the Rate-Distortion function Rd is the minimum of all rates R for a given distortion d such that Rd is achievable. Then we fix d and minimize R over all achievable pairs Rd to conclude that Rd is greater than or equal to Ri of d. To prove the converse, we first let Rd be any achievable Rate-Distortion pair, that is, for any epsilon greater than 0 that exists for sufficiently large n and nm code such that the rate of the code is less than or equal to R plus epsilon, and the probability that the distortion between the source sequence and the reproduction sequence greater than d plus epsilon is less than or equal to epsilon, where x hat is equal to g of f of x. Recall that f is the encoding function and g is the decoding function. Now from this assumption, we have n times r plus epsilon greater than or equal to log m. Since m is the size of the codebook, we have log m greater than or equal to the entropy of f of x, which in turn is greater than or equal to g of f of x. And this is equal to the entropy of x hat. Now we subtract from h of x hat given x, which is equal to 0 because x hat, the reproduction sequence, is a function of x, the source sequence. And this is equal to the mutual information between x hat and x. Now we expand the mutual information between x hat and x in the other way to obtain hx minus hx given x hat. Now hx is equal to summation k equals 1 up to n hxk because the source is IID, and hx given x hat by the chain rule is equal to summation k equals 1 up to n h of xk, conditioning on the reconstruction sequence x hat and the source symbols x1, x2 up to xk minus 1. Now for this conditional entropy, it is upper bounded by h of xk given xk hat because conditioning does not increase entropy. What we have done here is to drop all the random variables in the conditioning except for the random variable xk hat. And this is equal to summation k equals 1 up to n h of xk minus h of xk given xk hat, which is equal to ixk xk hat. Now this mutual information between xk and xk hat is lower bounded by Ri evaluated at expectation of the distortion between xk and xk hat. This follows from the definition of the function Ri, because by definition of Ri, for any xk hat achieving the expected distortion between xk and xk hat, the mutual information between xk and xk hat must be at least equal to Ri evaluated at that expected distortion. In the next step, we multiply the summation by 1 over n and then by n. Then by invoking the convexity of the function Ri, we obtain the lower bound n times Ri of 1 over n summation k equals 1 up to n, the expected distortion between xk and xk hat. Here, what we have done is to move the averaging outside Ri into Ri. Now 1 over n summation k equals 1 up to n, the expected distortion between xk and xk hat, is simply the expected distortion between the source sequence x and the reproduction sequence x hat. Now let d max, where this d is the small d, be the maximum of dx x hat over all x and x hat. That is, d max is the maximum value in the distortion table. Then the expected distortion between x and x hat is equal to the expected distortion between x and x hat given dx x hat is greater than d plus epsilon times the probability that dx x hat is greater than d plus epsilon, plus the expectation of dx x hat given dx x hat is less than or equal to d plus epsilon times the probability that dx x hat is less than or equal to d plus epsilon. Now the expectation of dx x hat given that dx x hat is greater than d plus epsilon is at most equal to d max by definition of d max. And the probability that dx x hat greater than d plus epsilon by our assumption of the code is less than or equal to epsilon. And the expectation of dx x hat given dx x hat is less than or equal to d plus epsilon evidently is less than or equal to d plus epsilon, and the probability that dx x hat is less than or equal to d plus epsilon is upper bounded by 1. And so we obtain the upper bound d plus d max plus 1 times epsilon. That is, if the probability that the average distortion between the source sequence x and the reconstruction sequence x hat exceeds d plus epsilon is small, then the expected average distortion between x and x hat can exceed d only by a small amount, because in the above, d max plus 1 is a constant. And so, if epsilon is small, then d max plus 1 times epsilon is also small. Summarizing the above, we have n times r plus epsilon is lower bounded by n times ri, evaluated at the expected distortion between x and x hat. Now we cancel n from both sides to obtain r plus epsilon is greater than or equal to ri, evaluated at the expected distortion between x and x hat. Now since the expected distortion between x and x hat is upper bounded by d plus d max plus 1 times epsilon, we obtain the lower bound ri evaluated at d plus d max plus 1 times epsilon, because ri of d is non-increasing in d. Now observe that ri of d being convex implies that it is continuous in d. By letting epsilon goes to 0, we have r greater than or equal to the limit as epsilon tends to 0, ri of d plus d max plus 1 times epsilon. By continuity, we can move the limit inside the function ri so that this goes away, and therefore we have r greater than or equal to ri of d. Finally, we minimize r over all achievable pairs Rd for a fixed d to obtain Rd greater than or equal to Ri of d. This completes the proof of the converse of the Rate-Distortion theorem.